My name is Kevin Lee. I am the lead deep learning engineer at Building Diagnostic Robotics, a startup looking to advance building envelope inspections using AI and robotics. I'm also a graduate alumnus from the Computer Science Master's Program at NYU Tandon School of Engineering. The work I'll be presenting today is a joint collaboration between BDR and NYU Tandon's AI Forest Laboratory, headed by my former master's advisor, Dr. Chen Feng. Today, I'm excited to be presenting to you all what we're calling GPR-Former, our improved context-aware moisture detection system for building rooftops using ground-penetrating radar. I'll be going over the significance of moisture detection, the existing methods and their limitations, how we went about our first attempt at this task, and ultimately how we took what we learned from that attempt and applied it to designing GPR-Former. So let's get started. So let's start by understanding why moisture detection is such a critical problem. Moisture damage is both widespread and costly. A recent study shows that 1/3 of all energy used in buildings in the United States is wasted, which amounts to approximately 150 billion US dollars in lost costs annually. As for structural integrity, well, where there's water, you can expect it to be rot and corrosion, which significantly can undermine the integrity of critical building components and shortens their lifespan. As far as health and safety are concerned, approximately 21% of all asthma cases in the United States can be directly attributed to indoor mold. And depending on where you are, regular maintenance might not just be best practice, but it can also be a regulatory requirement. Where we're based in New York City, buildings have to adhere to what's called Local Law 97, which is a part of the city's broader push to lower or eliminate greenhouse gas emissions by buildings in the city. And so all in all, failing to address moisture damage is not only harmful to our health and our wallets, but it also undermines our sustainability efforts and the broader push to a circular economy. So let's turn our attention to the rooftop today. So why do we focus on rooftops? Well, the reasons are twofold. First, the disproportionate costs and failures. Re-roofing a low-slope commercial building can run you anywhere from $3 to $15 per square foot, depending on the type of roofing. And if you happen to own or are responsible for a medium to large commercial building, you could be looking at a 6 to 7 figure roof replacement bill. A recent US EPA study surveying 100 randomly sampled commercial buildings across the United States found that of the 100 buildings surveyed, 55% of the roofs have suffered moisture damage in the past, and a third of them continue to suffer moisture damage at the time of the study. The second half of our motivation is that rooftops are among the components of a building, they're relatively easy to access and monitor. They can accommodate, or they are navigable by drones and robots, and can accommodate a variety of sensors and inspection methods. Because of this combination of high risk and high accessibility, rooftops become a natural starting point for our investigation. So let's look at some of the existing methods that are being used for moisture detection on rooftops. By far, the most surefire way to tell if there is a moisture issue on a roof is to take what's called core cuts. And this is when you physically cut out a section of the roof to inspect for moisture. Now, while we can easily determine if the material is wet, this is obviously a destructive procedure, and destructive procedures may not be the most desirable for building owners and other stakeholders. And so to address this, there are a host of non-destructive techniques that people have developed over time. Let's take a look at one called infrared thermography. Infrared thermography, or IRT, uses thermal cameras to capture the thermal radiation emitted from a rooftop surface. Now, this works because materials saturated with water tend to have a higher thermal capacity compared to when they are dry. Wet areas would show up as hotspots with high contrast due to the retained heat from, solar energy throughout the day, making them easy to spot. And so this makes IRT a relatively easy technology to interpret. Recent works have even expanded on the ease of interpretability of IRT through the integration of visualization technologies like BIM and 3D mapping on point clouds. However, IRT has some downsides. It is highly sensitive to environmental conditions like the weather and the time of day. Furthermore, it is typically recommended to confirm the results via core cuts anyway. So in the end, IRT is an effective tool for screening, but it's usually not reliable on its own. So where IRT fails or is otherwise inadequate, you might turn to something called electrical capacitance surveys. Now, EC meters, electrical capacitance meters, detect moisture by measuring the changes in the dielectric properties of the surface being scanned. And surfaces saturated with moisture would have a higher dielectric constant than their dry versions. These sensors are typically portable. Some simple versions can be affordable. And the great thing about them is that their results are, if calibrated properly, are very immediate and rapid. However, there are some significant limitations. They cannot be reliably used to sense moisture at depth below the surface. They typically require direct contact with the roofing membrane. And probably the most important limitation is that they cannot be used on some rubber or conductive membranes like EPDM. So in the end, EC surveys definitely have their merits, but they are limited in their scope and inability to sense deeper signals. So next up, we have an actually rather effective method called nuclear moisture gauges. But if you can tell the pattern, I think you can come to expect or see what to expect. Nuclear moisture gauges work by emitting fast-moving neutrons via radioactive decay and counting the rebounding neutrons that collide with hydrogen atoms in water molecules. And so surfaces saturated with water will, of course, have a higher concentration of hydrogen atoms present. This method is great. It can sense signals at moisture signals at depths. It is relatively unaffected by environmental conditions, and it has even standardized testing protocols in the United States. However, operating them can be rather labor intensive, and most importantly, as you might have guessed, they require specialized licensing, training, and compliance with regulation. So yes, NMGs can be effective, but they can also be somewhat of a headache to use in practice. So each technique here leaves a gap. Core cuts are destructive. IRT is highly sensitive to environmental conditions. EC surveys are limited in scope, and nuclear moisture gauges require quite a bit of overhead. We need a method that is non-destructive, can sense subsurface moisture signals, can work on a wide variety of roofing structures, and can be ideally integrated in automated mobile platforms. So let's take a look at ground penetrating radar. So for those of you who might be unfamiliar with the technology, ground penetrating radar, or GPR for short, uses electromagnetic waves to detect changes in the dielectric properties of the materials the waves propagate through. This is similar to the way EC surveys operate. However, we are able to penetrate deeper into the surface of the roof. There's an antenna that emits electromagnetic waves and a receiver that reads the amplitudes of the reflected waves. GPR is commonly analyzed in 1D, 2D, and 3D forms. For 1D, we have what's called an A scan, and this is just when you have your sensor and you emit the wave and record the reflections for a point scan. Now, if you take that GPR sensor and you move it over a bit, take another A scan, and you keep doing this over and over again in a straight line, you have what we call a B scan. And this is our 2D representation, and it is typically interpreted or analyzed in the form of an image. Now, if you take these B scans in parallel and have like a grid-like structure, you have what's called a C scan, and this is our volumetric representation of GPR data. And so just to illustrate what this might look like on a rooftop, here we have our C scan and an image of some rooftop. And we just put that rooftop on the C scan. You can see that the X and Y plane represents the roof surface, while depth is plotted on the Z axis. And so on a roof, high amplitude reflections might correspond to material boundaries, be it objects, insulation layers, or maybe more importantly for us, moisture saturated materials. So how does GPR actually detect moisture? If you recall the part about capacitance meters, GPR again is very similar. It detects the changes in the dielectric properties of the subsurface materials that the waves propagate through, which spike when water is present. But unlike capacitance, GPR is able to detect subsurface moisture, like hidden water pockets. And recent works, and even one of our own, shows that GPR can be integrated seamlessly with mobile platforms like drones and robots, making it good for automated inspections. With automated inspections, we might run into scalability concerns, but we can rely on deep learning to address that. So taking these ideas, our team developed what we call Rufus, a robotic platform that provides end-to-end moisture mapping using supervised learning. With Rufus, we were able to analyze GPR B scans using deep learning to detect moisture with high accuracy. And we actually use the system on multiple real-world sites and roofing systems, proving its effectiveness in automating what used to be a very labor-intensive process. However, of course, Rufus was not without its limitations. One of the biggest issues was what we call local signal obfuscations, which basically is just strong reflections from surface features that could mask the surrounding moisture signals. We found this to be a significant problem because of our B-scan-based approach, which had rather limited visibility outside of its somewhat linear scope. We also observed that water damage and just the way the water propagates tends to form or manifest in these radially shaped clusters. And so this led us to wondering if we should utilize the added spatial information afforded by C-scans. However, we found it difficult to integrate C-scans into our process in practice. To make effective use of C-scans, the underlying A-scan must be accurately aligned, and this proved somewhat challenging at scale, especially due to sometimes complex and irregular pathing our robot has to make due to the construction of rooftop and surface structures. And so this led us to ask, is there a way we can take advantage of C-scan-like analysis without having to adhere to the somewhat rigid requirements of constructing them? And so this leads us to GPR-Former, our transformer-based architecture that introduces the idea of using position-encoded A-scans to accomplish tasks requiring C-scan-like context. We'll be going over briefly the key features of transformers that make this possible, how we partition rooftops into groups of spatially coherent A-scans, and then lastly but not least, how we encode the positional information into the GPR signal features. So why transformers? Well, it's no secret that transformers have been revolutionizing domains requiring an understanding of sequences and leveraging positional information, like in natural language processing and in computer vision. Our work in Rufus showed that transformers can also be effective in processing GPR data. Moreover, Rufus demonstrated that rather than analyzing GPR B scans as images, as was typical, we could interpret B scans as a sequence of the underlying A scans, kind of like words in a sentence. So if we want to take this to the C scan level and extend it, why can't we do the same by interpreting a C scan as a group of the underlying A scans accompanied by their positional data? So the key that makes transformers so effective lies in the self-attention and positional encoding mechanisms. You can consider self-attention like a sort of pairwise operation where every A-scan in its group can inform every other scan in that group about the information that it contains. And so, for example, if there's a scan with a strong reflection some 30 centimeters away this way, that might contextualize how a scan might have a weaker echo over here. And so to better visualize how self-attention might work for us, on the screen, we have an example of a region that has moisture damage. And ideally, the attention mechanism would ascribe higher weights to the important regions that indicate moisture signals. So we get our positional data for each scan from our hardware and robotics side of things, so that part is covered. Now we just need to form these scans into groups for the model to ingest. We're going to go about this using a KD tree for a KNN-based clustering approach, where each cluster or group in our case will consist of a seed scan and its group size nearest neighbors, and we call group size omega. We identify omega as an important hyperparameter. If omega is too small, there might be groups that are entirely within the same B-scan because they fail to overcome the gaps, the distance between each B-scan. And so if this is the case, then there's no real difference than our Rufus method. So this is not ideal. And if omega is too big, we might introduce artifacts, grouping artifacts like disjoint groups that are separated by a large space due to the stochastic nature of our procedure, which again, we think will hinder performance. So now that we have our groups of A scans, we need to somehow embed the positional information into the signal features. So this brings us to the process of positional encoding. Positional encodings are important because transformers do not innately have any sense of order or structure, position. Think about how in language, the order of words fundamentally change the meanings of a sentence. Positional encoding injects this positional information about each word into the model, thus enabling the transformer to capture the sequential structure and relationships within the data. In our case, we'll be injecting the information about the A scans X and Y positions into the model, dedicating half of the signal embedding to X and the other half to Y. And in our implementation, we test three strategies: a sinusoidal absolute encoder, a rotary encoder, and a learned encoder. And we test these approaches just to see what information is necessary to accomplish what we are aiming to do. The sinusoidal method is the base approach, capturing the absolute positional information. The rotary encoder, we investigate if adding relative positional information will be beneficial. And with the learned encoder, we are looking to see if our model can determine the optimal encoding strategy from the data itself. And so for our experimental setup, our dataset was sourced from a 46,500 square meter retail complex, covering multiple roofing systems and membranes, including modified bitumen, EPDM, and TPO. From this building, we were able to collect just shy of 900,000 labeled GPR-A scans. And we divide the data into training, validation, and evaluation sets by building section. We also tested 3 different sizes of GPR-Former: base, large, and huge, to benchmark the performance and parameter efficiency. So here are our experimental results. GPR-Former delivered consistent performance improvements across all metrics in average recall, F2 score, and area under the receiver operator characteristic. The metric we would like to highlight is the 6% boost in average recall over our prior Rufus model. We find that when it comes to rooftop repair and replacement, while precision is absolutely important, we might find that it is preferred to prioritize minimizing the number of false negatives. We would prefer a scenario where we have to rip out a little bit of extra non-defective roofing if it means we absolutely cover and identify all of the truly defective roofing. Our results also show that GPR-Former achieved all of this while being 2 to 7 times smaller in terms of parameters. Further improvements to efficiency here might bring us closer to eventually being able to have all the moisture detection done on board on the robot in real time. And on the right-hand side of the screen, we have the qualitative results. And this is a comparison between the outputs, the segment-activated outputs of GPR-Former and Rufus over the ground truth portion. And you can see from the diagram itself, blue indicates the presence of moisture and the reddish sections indicate no moisture. And you can see that GPR-Former produces much more confident and a wider distribution of scores, meaning that it was both more reliable and easier to interpret, which are important factors for real-world adoption. As for testing some of our hyperparameters, we tested which values of omega and which positional encoding strategy produced the best results with using validation data. And we found that the optimal performance was achieved using omega equals 1024. Performance was relatively stable between the values of 512 and 1536, only really deteriorating for extreme unrealistic values. We also determined that the sinusoidal encoder performed the best of the 3 encoding strategies. And so to summarize our findings, our work validates that using a transformer on position-encoded A scans can be an effective alternative to the typical methods of processing GPR B scans and C scans, in the B scans case as images and C scans as a volume. And furthermore, we believe that GPR-Former should be directly generalizable beyond just moisture detection to other GPR targets like in rebar and in utilities detection. The concept of GPR-Former is to provide a more flexible alternative to processing GPR data. So any task that might benefit from a 3D perspective should apply. Of course, our work still has some limitations. We believe that we could greatly benefit from a larger and more high-quality labeled data set or from more diverse sources, like buildings with membranes that we have not covered in our study. We're also interested in not only detecting the presence of moisture, but also localizing the depth and the severity of the damage. And so these limitations guide our direction in exploring future works to further improve upon our model design. And with that, I'd like to thank you all for your attention. I'd like to acknowledge the support of the National Science Foundation and my colleagues at Building Diagnostic Robotics and at NYU. And if you have any questions or are interested in our work, please feel free to contact us through any of the information shown on the slides. And I'll also be around to chat.